Hello, Dr. Mohammed. How are you?
Hi, John. How are you?
My name's John, and I'll be today curating this webinar, and I hope everything's fine from your end. So please, you can start.
Thank you, John, and the team for the kind invitation to communicate with your club and your audience to give this webinar about our latest research and how we can translate the fundamental research we are doing in the lab into real world applications. So we will start talking about the attosecond electron imaging and why this electron imaging is important and why it's in attosecond and everything. And what is the tool we are using for this imaging? What is the potential application in the future, not just in material science or physics or engineering, but it could be extended also to chemistry and biology applications. How is this all starts? Science is not separated from the normal life, and the development happen in the new life. So in the old days, when we talk about information and when we talk about uh, 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 new things, we usually go to read in a newspaper or we talk about listening to the news in the radio all the old times, all the old days. But now as the technology developments happen in our community, everybody has in his own pocket now and a camera connected to the internet. So it's much easier to take images because images will give you a full detail about the event, whatever this event, even if you are going for a trip and you'd like to share your memory with your friends instead of going back and explain for them how the mountain you visited was amazing or the lake or the beach. Now you can take just an image, send it to your friend in a second, and they will get a full picture. Exactly the same happened in science. And instead of doing a lot of experiment and try to explain, if I able to give you an image of a physical phenomena happen, this will give you more details. But so this is explain the importance of imaging, but how is the story starts? The first imaging experiment has ever been done was done in Egypt next to you guys in the downtown Egypt about 1015 years ago or more. So this done in the market in the downtown Egypt. And when the people was passing by, there's a small room which was closed and just having a window with a hole here. And they start to look from outside to the hole. Then they hear noises, see something is moving inside, but they don't understand what it is. And they interpret this as normal people when they don't have enough science about what's going on. They say we are seeing ghosts in this room, and everybody was going away from this room until a man who's really a pioneer scientist. Probably most of you know his name is Al Haytham or Hussein in English, and this man has a fantastic books of optics, which is the basic principle of all the optics and lasers we are studying today. So this man, when he passed by this small room, he think about it with a scientific mentality. Then he did this simple experiment. He get into the room and he put this white screen inside and he looked to the hole and he see an inverted image of this mosque here on the screen. And then he started to explain this as a principle of camera obscura. This was the basic principle of the first imaging experiment ever happened in the history. Okay, and even the name, the hole in the window here in Arabic language, it's camera. Any hole in a window, it's called the camera. And this is why it transferred later on to a camera, which everybody knows now. So the name coming from Egypt and coming from this pioneer experiment. But this is about taking an static images. What about taking videos or moving or imaging the moving objects? For that, we have to fly from Cairo, Egypt to California, US. This happened in the end of 19th century, and a very interesting experiment. There was a businessman, and he was also the governor of California back to the time. And you know his name. His name is Stanford, and he's, yes, the founder of the Stanford University, very famous Stanford University. And this businessman was obsessed with horse racing. And he had a horse he loved so much. And he had a theory that his horse is so fast, such he's flying at a certain point of time during the racing, and all of his four feet are off the ground. But he was not able to prove that to his friends and his community. So what he did, he tried to take some images, but the images were so blurry, so there was no proof. Until he hired this scientist, Muybridge, okay? And he asked him to solve this problem. Muybridge hired some engineers from Bay Area, from California, to work on enhance the speed of the camera shutter. This is an important point. So before they're working with a camera speed more than milliseconds, but these engineers for the first time able to make a mechanical shutter open and close in less than 1 millisecond. And he repeated the experiment, and he took these different snapshots of the horse. And because the speed of the shutter was faster than the speed of the horse, he was able to take a nice clear images, snapshots of the horse, where, like, if you see here and there, these two snapshots show that Stanford was correct. The 4 feet of the horse at a certain point in time are off the ground. So, and he published this in Nature in 1882. What is the take-home message from this? If you would like to image and a very fast moving object, your speed shutter has to be similar or faster than this object movement to be able to take in a clear image. And this was a basic principle later on for starting a new type of science or a new field of science called ultrafast science. And since we are limited in the mechanical shutter of normal camera, it cannot go beyond the microseconds nowadays. So we are missing the capability of imaging faster object motion like electrons, atoms, and molecules, which happens in picosecond time scale 10 to minus 12, femtosecond time scale 10 to minus 15, or attosecond time scale 10 to minus 18 of a second. This is why by the end of the last century, they invented a new technology or a new methodology called freezing time or times of spectroscopy. So instead of using a shutter, mechanical shutter camera, they are using a laser as a shutter for your camera. So what they are doing, they are using 2 laser pulses. One of them is to trigger the dynamics happen in this target, and they are imaging or they are recording the effect happen on the probe pulse. Okay, and in this case, the resolution of your snapshots depends on the pulse duration of your probe pulse and your pump pulse. So you are taking a spectrum of the probe as a function of different delay between pump and probe. In this way, you will be able to have a snapshots of the dynamics happen in this target pumped by this laser. Then you can go back and see how this affect the spectrum at different time. So you are introducing the time axis in this case. You go to your theoretical colleague, ask them to interpret the spectrum change. and relate this to the motion happen inside this target. And this is called freeze-time or time-resolved spectroscopy. Here, the shutter is the Broad pulse, and the Broad pulse duration defines the resolution of your capturing. So this is a Navier graph show the progress happened in ultrafast science since 1982 or 85 to be accurate, when the first experiment done with famous Ahmed Zewail, when he was able to trace the atomic motion inside the molecules in few hundred of femtosecond or picosecond time scale. And for that, he got recognized by the Nobel Prize in 1999, and he introduces a new subfield completely under the ultra-fast science umbrella, which called the femtosecond or the femtochemistry. This is about the atomic and molecular motion, but we have another motion which happens in faster time scale. So the scientists started to work on enhancing the resolution, the pulse duration of the lasers to able to capture the electron motion inside atoms, molecules, and nanostructure. And by the 2001, they able to generate attosecond laser pulses, and laser pulses which has a duration of less than 1 femtosecond. And this is similar to what happened in femtochemistry, introduce a new science which called attosecond physics. And these new tools enable us to trace the electron motion in different systems, and also got recognized in 2023 with the Nobel Prize in Physics. Why electron motion needs an attosecond resolution? Because the electron motion, the native time of the electron motions happen in few hundred of attosecond or few femtosecond. So as we learn from the horse experiment, you need to have similar speed to your electron. So you need to have an attosecond speed to be able to image electron. What we try to do is not just to take this through the spectrum measurement. So let me explain this in a different way. When you take a spectrum measurement church and go back and try to trace it back and see how this related to your electron motion, it's similar to the old time when you take an analog image. You are so young, you don't remember that, but the beginning of the millennium, we were still using a film inside a camera where you take images and you have a negative and you have to go to the job and convert it to images. Now we are hoped by what we are introducing in attosecond electron microscopy imaging to replace this digital analog camera with a negative to a new digital camera, as you can see here, which give us the electron image right away. Why electron motion is important? Electron motion is everything in our life. Just a very important example, electron motion is converting or controlling the forming of bonding between atoms inside the molecules. So if you are able to see something, you are able to control it. If you're able to see this electron motion, which forms and break bonds, we can control these bonds, control chemical reactions, control the synthesis of molecules. And this has a huge application in designing new drugs, treatment of diseases, and a lot of things. The part which you may be interested more, the capability of controlling the electron motion inside solid states will enable us to control the current motion inside this material. And if we're able to control this electron motion and the current introduce or induce inside the material with the speed of light, we are changing the speed of electronics completely, because we are switching on and off the current with the speed of attosecond laser pulses, not anymore with the voltage which maximum happen in nanosecond time scale. This answers the question of Dawn. He was asking before we started the webinar why we are talking about phototransistor or photon, generally speaking, because the light field of the laser pulse has the capability for controlling current in much faster time scale and enhance the speed of electrons. So let's start to think how we can image the electron motion. The best tools has been invented so far for imaging in our in science, generally speaking, is the transmission electron microscope invented by Knoll in 1932, and he received the Nobel Prize for this in 1986. Together with other scientists who were able to introduce or develop or invent the scanning tunneling microscope, which able to introduce better spatial resolution to our transmission electron microscope. And in fact, this two powerful imaging technique has opened the door for a vast range of applications in not just in physics or material science, but it's extended to chemistry and biochemistry, particularly with the development happened later on by introducing the cryo technology to the transmission electron microscope and able to see the structures of protein and get a Nobel Prize in chemistry in 2017 for this development. Okay, now transmission electron microscope is still using the mechanical shutter of camera, which is switching on and off, very slow time scale, around microsecond time scale. How we convert this to time resolve, ultra fast electron microscope. This has happened actually by first convert instead of generating a continuous wave of electrons inside the microscope, we replace that by introducing an UV laser to illuminate a photocathode here and generate an ultra-fast electron pulse. Again, here we would like to generate it in pulses to enhance the resolution, temporal resolution by using this ultra-fast electron probe pulse as our shutter. And then we are using the bump. So this is similar scheme like time resolve measurement. One probe pulse here, UV generating electron, and bump pulse, which is the laser. The bump laser is triggers the dynamics, and the probe electron pulse is imaging this dynamics. The first invention of this ultra-fast electron microscopy happened in Technical University of Berlin in 2000, where they are able to use a few nanosecond laser balls to generate nanosecond electrons, and they're able to see the melting of nickel phosphate thin film. What you can see here is a snapshot of this melting of this thin film. Then Zewail group at Caltech was able to enhance the temporal resolution inside the electron microscope to femtosecond time scale. And this opens the door for many applications. I'm just giving you some of the examples. We're able to use this for, or the community or the Zewail's group able to use this for imaging thin film gold phase transition in picosecond time scale, and this is what I will show you here in this video. This is a phase transition in gold happen in real time in picosecond time scale, transferred from one phase to another. We use also this, or it has been used as technology for imaging the laser trigger mechanical motion inside a carbon nanotube. So you can see this motion happen here in nanosecond, triggered by the laser. You can see the wiggling. You can see the breathing of this nanostructure movement under the microscope. Also, the microstructure shape memory alloy was able to image, as you can see here, in 2010, and as you can see, we triggered this dynamics with laser, and we're able to see the motion of this nanostructure in the alloy, or even imaging the phase transition on one particle of a metal organic particle as you can see it in this movie, also happen in nanosecond time scale. You see the laser able to convert the or do induce and a phase transition in this one particle, as you can see it here under the microscope. So the beauty of this, you can image something not visible by eye, but you're able to see it. This is also extended to the mechanical motion of DNA, as you can see it here. There's a DNA, and we're able to see how this DNA dynamic motion happen under the microscope, also imaging an amyloid beam moving into space and time in microsecond time scale. So all of this technology or all of these applications has been demonstrated, but also there was another breakthrough when we able to image nanoparticles in a liquid cell. And why this is important, you hear about the drug delivery all the time, the capability of nanostructure to carry drugs and go inside the body, but the environment inside the body is liquid, right? So it's very important to understand how this nanostructure moves inside the liquid phase. And this was the first experiment showing that the capability of motion of nanoparticles, gold nanoparticles inside a liquid water, and this has been seen under the microscope as well. Also, there are other technology or other techniques can be used for imaging, like electron energy loss spectroscopy inside the microscope, and you're able to trace the carbon-carbon atom strands inside graphene, but this is in a spectroscopy mode. Okay, we are, if we go back to the electron microscope, the temporal resolution of our imaging is restricted with the electron pulse duration, which means if we're able to image, back again to the horse experiment, if we're able to image fast motion, we need shorter electron pulse. But we have a small problem with that. Electrons are charged particles, right? And when they move from the position of generation in top until it reaches to the sample, there are repulsion force happen between these particles, which make it in a space spreading out, and the duration becomes long. And this is a big technology challenge inside the electron microscope. Okay, how we can solve that? The best resolution we're able to reach is 500 femtosecond. It's enough to image atoms, but it's not enough to image electron, which is our main goal. So this was a very serious challenge until 2009. Again, in Zewail's group, they discovered there are a coupling happen between the laser and the electron. What does that mean? The electrons coming from the microscope with the laser hitting the sample are a changing momentum. And when they change a momentum, they are the electron itself are gaining 1 photons, 2 photons, 3 photons, or losing 1 photon energy, 2 photons, 3 photons, which means there are side peaks of electrons here are formed when only the laser is shining. If you switch off the laser, you get the black spectrum. When you shine on the laser, you see the red spectrum. What does that mean? That means this side peaks here is only exist in the presence of the laser pulse. What also that mean? That means these electrons has a temporal resolution similar to the laser. I will explain this in more details. But generally speaking, the idea of coupling between the electrons and the laser has been used to image surface plasma dynamics inside silver nanowire. This is a nanowire you see, and this is a scattered light around the surface of, you are hearing all the time about surface plasma, the scattered of light from the membrane or the surface of silver nanowires. Here is this. This is a clear image of it. And if you would like to see how is a scattered electron on a bow tie shape of silver nanostructure, this is how the distribution of light or surface plasma happens. So all of this technology or all these applications opens the door later on for what we called optical gating. What does that mean? As I explained earlier, when we have a gating happen between the electrons and the laser, we see this side bands I'm showing here in violet and green. Okay, this side bands has only formed when the laser is overlapped with the electron pulse. Okay, so I have two types of electrons now. One comes from the cathode, the one in black blue, and the side peaks, which is here in the faint blue or baby blue. Okay, they have both different timbre resolution. The dark blue has a very long pulse duration. The side bands here has a pulse duration similar to the laser. So we're able to then generate electrons very short, similar to the duration of the laser pulse on the sample, which solve a huge problem for generating in a very short electron pulses. We can filter out this gated electron with the laser, which has a very short time or very short pulse duration, and use it as a time resolved measurement, trigger the dynamics by another laser pulse, then measure this dynamics with a microscope, either with diffraction or a spectrum or any means of electron microscopy. So this is a new thing. I published it in 2015 with Zewail, the capability of generating shorter electrons with optical gating. Okay, we need to test that. So what you can see here, this is electrons. This is the gated electrons, which you can see it here on the side. And the ungated electrons has a duration of 540 femtosecond. And I use an laser pulse of 200 femtosecond to gauge these electrons. And we able to measure the gated electrons only timbre profile. Cross correlation is 280 femtosecond. If you multiply this by square root of 2, so this will give you the gated pulse duration, which is 200 femtosecond. So the idea works of optical gating. This was the first basic principle, and we use this gated electron to see the dynamics of vanadium dioxide by the means of diffraction, and we see similar behavior like non-gated electrons. So this was the first proof. Gating idea is working, but now we do it with 200 femtosecond. Can we do it with shorter laser pulse? And for that, we use shorter gated laser pulse, 30 femtosecond, and instead of 200. And we gate electrons with very short time scale. Then we try to see if it's really gated in 30 femtosecond time scale. We measure the cross correlation. You see this dip here in the electron related to the gated electrons. And when we extract the duration, we find out that it's really 30 femtosecond, similar to our laser, which is very good news, because now we are going shorter and shorter. We are breaking the limits, and we are going to our dream to have sub-femtosecond to be able to image electrons. But as a scientist, you need to prove that is not just giving the results you want. So yes, 30 femtosecond is perfect. This is what we want, but we had to change the duration of the laser and see the effect. And when we make it longer, the duration of the electrons becomes longer. So you can not just prove your experiment results, but getting what you want, but also to sort of messing up with it and prove it's also responding and follow your ability to change it from long pulse to short pulse. And this is what we did in this experiment. So as I said, this is a view graph for the enhancement of timbre resolution in ultrafast electron microscope, starting in 2000 with the first ever ultrafast electron microscope, 10 nanosecond, which was able to see phase transition. Then Zewail enhances timbre resolution to 500 femtosecond, able to see or cover the atomic and the molecular motion. There was many other technical development to enhance the photocathode preparation, but this is lead us to 200 femtosecond only. But the first breakthrough happened when we able to gate it with 30 femtosecond, as I showed to you, but we are still far from the era or the scale where we can see electron motion, because it requires us to enhance this 30 times more to be less than 1 femtosecond. And this is what we did recently in 2024 in this reference, and reaches 625 attosecond. And this is what I'm going to explain you later. So the capability for enhancing the timbre resolution to attosecond time scale, or to introduce what we call attomicroscopy or atomicroscope. This is we done by, we agree, as I explained earlier, then if you're able to gate the electrons, the gated electrons will follow the pulse duration of your gated pulse. That means if you're able to gate with sub-femtosecond laser pulse, you will be able to generate sub-femtosecond or attosecond electron pulses. And this is exactly what we've done here. We use our tricks with lasers, because we are like laser wizard, to generate a half-cycle laser pulse with a pulse duration of 625 by playing with the polarization of two lasers until we get this gated electrons, which has 625 attosecond. And we send it together with electron pulse here to generate gated electrons with sub-femtosecond resolution. Then we bump, as a first proof of principle, use another laser pulse to trigger the electron dynamics inside graphene, and to try to see if our gated electrons can see this electron motion inside graphene. Let me explain to you what happened when we trigger the dynamics of electrons inside graphene by laser pulse. So probably you studied this in earlier time in high school or undergrad, when we are shining a laser to a system in the ground state, it got excited to the exciting state. And this is by absorbing photon and enhance the electron from here, or excite the electrons from ground state. Here is the valence band to the conduction band. And this photon-induced dynamics, which we call it interband dynamics. But because the laser field itself here has a certain potential, so the electrons in the presence of this electric field is moving, oscillating inside the conduction band, following the shape of the laser pulse. And this is the sub-femtosecond electron motion, which we are interested in, which called an intraband dynamics. Okay, so let's see how this electron distribution inside the conduction band looks like in the presence of the laser. At the beginning here, we have some photons, but not too much. And this is excite some electrons to the conduction band. And this is why in this 3D, you see some excitation of electrons, right? The red here means the number of electrons, okay, is high. And we excite here, okay? Now let's move on with our cursor here to see what happened when we reach it to this point in time. You see the distribution of the electron in the conduction band, the number increases. So it's not anymore around 0, 0, but increases to the positive and negative side. The distribution is also different. And it's affected with the amplitude and the direction of the electric field. So which means there are an electron dynamics happen in the conduction band. But how this reflected back to the real space? Before we go to the real space, I will show you a video about the electron distribution in the presence of the laser pulse inside the conduction band. And this is how is the electron distributed in this conduction band. Beautiful, right? I mean, this is very nice. Electron dynamics happen with laser pulse. But this is in the conduction band. How this is affecting the electron motion between the carbon atoms inside graphene. To see that, we went to electron diffraction. This is not updated, this is published already. So we record the electron diffraction pattern. First order, you can see it here. First order diffraction pattern of graphene. This is the second order, and this is the third order. So we record this electron diffraction, and we see how this electron diffraction intensity is changing over time in our measurement. So you see it starts nothing, then the diffraction intensity is changing related to the electron distribution in the conduction band. First order, second order, and third order, we fitted this measurement to the interband and interband dynamics, which I explained it earlier. Then we retrieved back accordingly how the electron distribute between carbon atoms inside graphene in real space. What you see here is 6 carbons, 1, 2, 3, 4, 5, 6, which exist in graphene. Okay, and I named them B1b, A1, C1c. Now I invite you to look between these 2 carbon atoms and see how this is changed at different time when the laser pulse is present. So when we are here, you can see the electron distribution here is different. More electrons are pushed around B atom and less around B dash. I can flip this by the laser and make the distribution is almost equal, okay, at this point in time, then completely different, push all the electrons from B dash to B. So, and move on, and this is a retrieved video of how the electron moves between carbon atoms in the presence of the laser as a function of time. You see the electron distribution between carbon atoms. Black and blue means it's very small amount. Red means very high amount. I will run it again to make you focus on it, see how the electron distribution change between carbon atoms here. So this is how the electron moves in the graphene. We can, if we can, as we explained earlier, if we can see it, we can control it. So now we are using this laser pulse, you see it here, and measure the diffraction, trigger the dynamics inside the carbons, and we see at this point in time, at 0 time, all the electrons are moving from C1 to C2. If I flip the shape of the laser pulse, I flip the motion of the electron from C2 to C1. So I have a full control using a laser pulse on the electron motion between the carbon atoms. And this capability of attomicroscopy of imaging electron motion opens the door for huge applications. This is why I call it Rosetta Stone. Rosetta Stone used to translate a different language, Latin and English, and holographic, to allow us to reveal the secrets of the pharaonic culture. This is similar. This is attomicroscopy is a Rosetta Stone, will make us understand how the electron moves inside molecules, inside the materials, and reveal the secrets of the material itself. And it can be used in huge number of applications. And this is applications I summarize in this paper. But let's see in real life, we talk about this at the beginning of the webinar, how we can convert a fundamental science, which we so far showed to use the capability of imaging electron motion inside graphene, to a real life application. This is what we have done. When we understand the electron motion in graphene, we understand how we can control it with the laser pulse from the previous experiment. Now we use it for real application by developing the Petahertz quantum current switching or Petahertz quantum phototransistor. So we have this commercial graphene phototransistor. It has this composition. It has one layer of graphene underneath and a layer of silicon dioxide, 50 nanometer, then a big layer of silicon. There are two gold balls here to transfer current or to measure current between them. When we shine laser in the beginning, we don't see any current. And the reason is graphene is symmetric. So you don't build any potential difference. So you cannot transfer current or electrons from this side to this side to be able to measure current. This is why we have zero current when we shine with the laser. But when we did some modification on this graphene to break the symmetry, and we introduce a layer of silicon to break the symmetry between graphene, and we shine the laser again, we able to see a laser-induced current inside this transistor. So this was a first step, and it's very important in our measurement. Now we see laser-induced current. Where is this current coming from, and why we don't see it when we have graphene? Okay, we say because we have a symmetry, but now why, particularly, what happened exactly when we introduce the silicon layer? So in the beginning is a Fermi level of the two graphene is similar, but when we eliminate the graphene with laser, electrons are excited from ground state, from valence band to the conduction band. And this is in changes Fermi level direction and breaking the symmetry of graphene, not just by silicon, but also by the unsymmetric elimination of our laser spot here in the two sides of graphene. And when we measure the IV curve with no laser, I'm showing it to you here in blue color, and with the laser is on, I'm showing here to red. You can see there are a clear offset because of the light-induced current, 600 nanoampere. But when we also try to dig more and try to understand how this current is moving inside this graphene transistor, we subtract the two curves, the blue curves from the red curves, and it gives us this interesting curve. So this interesting IV curve is an indication of electron current tunneling happen inside our transistor. So what happened exactly is the electrons are excited in one graphene side. I can show it to you in this very graph, actually here. So what happened exactly is electrons are excited to conduction band, and because the potential of the laser, they are pushing the electron to tunnel through the silicon to the other side. And in this case, you are measuring positive current. And if the field direction is opposite, the electrons are pushed from the other side of graphene to tunnel through the silicon to this side of graphene, and the current in this case measure negative. And this is why when we have two laser pulses, okay, and we measure the generated current as a function of delay between these two laser pulses, we measure this modulation or oscillation of the induced current. Okay, and when we take the absolute value of this current, it doesn't matter if the current is negative or positive, it has an absolute value. And when you take this absolute value, you figure out that the current reaches to maximum at this point. Let's zoom in. The current reaches to the maximum at this point and minimum at this point. So we can say that the current here reaches to 30 nanoampere, and here to almost 1 or 0 nanoampere. Means the current can be controlled and switched on and off every 630 attosecond time, which is a first step for developing the attosecond switches or Petahertz switches. You do electronics and you understand very well the maximum speed now we reaches with semiconductor-based electronics is gigahertz. We cannot go beyond that. Moore's law is collapsing, is not anymore effective. and we need new electronics, new technology. And this is a new technology. I call it the electronics of the future. And the most important thing, we have done this experiment in ambient condition, means in the normal temperature and in the normal pressure, which is important because typically the experiment done in the lab is happen under certain conditions. But here we are talking about ambient conditions, so it's ready to be introduced in real life applications. We did simulation for the current. When we use graphene only, you see the generated current, because the symmetry of graphene is sum up to 0. But if we use the tunneling effect, we call it CAB, or the complex absorption potential, we introduce something similar to the tunnel in our simulation. We see a similar current to what we measure in the experiment. We can control the amount of or the percentage of the current introduced by light by increasing the intensity of current. We can control the the resistance in our graphene by laser light. We control it and drop it from 6 kilo ohms to almost 5.5 kilo ohms. So 0.5 kilo ohms drop just by eliminating the graphene with laser, and this corresponds to an enhancement of conductivity by 8%. We use this possibility also to demonstrate different logic gates inside graphene, and to switch on and off as a current and as external voltage to demonstrate certain logic gates. I think at this point, I would like to thank all our team members who put a lot of effort to reach these nice results, and our collaborators from different institutions and funding agencies. They fund our research. And I think I leave some time for questions. You are muted.
My bad. I was saying, wow, thank you for this very insightful talk. بجد استفدنا جدا. I have a few questions of my own, actually, to be honest. علشان انا برضو فاهم معظم الكلام اللي حضرتك كنت قلته، علشان انا دارس برضو حاجات كتيرة في electronics. My question to you is, do you think that phototransistors would replace actual transistors? And if
Yes.
how long would it take?
3 years, 2-3 years maximum. I mean, the people are the technology. We have a clear problem now, and the clear problem is we have a huge development in the software, artificial intelligence, machine learning. The hardware cannot keep up with that.
Hmm.
They cannot. Simply, they cannot. And all the market is searching for a new technology which could help them in performing this artificial intelligence, machine learning in much faster time scale. It's
Yes.
really big need and hunger in the community or the market for this new technology. So they are not just waiting for it; they are supporting it to be developed and be exist in short time. And when we, as a scientist, I can tell you for attosecond electron microscope, it may take a year to be in every lab. But for the Petahertz quantum phototransistor, because the needs on it everywhere in our life, because this is a real life applications.
Or طب, Doctor, regarding the power efficiency of this transistor, uh, what are we talking about? Is it low, high, medium, average? يعني
So explain for me كلمة power. Yeah.
the dynamic power,
نستخدمه.
the dynamic power, the switching power.
So
From
we have a switching efficiency of 30 to 1. Okay. And the laser power we are using is really very low power.
Okay.
So we are talking about milliwatts,
Hmm.
okay, of laser. So
Yes, yes.
this can be converted to micro amperes, which is huge.
Do you actually think that people can start integrating systems using these phototransistors?
We try to work on with industry to commercialize this.
So this is the next step, huh?
Yes.
Um, where do you see computing speeds heading in the next decade? Is it going to exceed the pentahertz or
Petahertz, yes, I think soon, because again, it's very anticipated. So petahertz is required, and I think in maximum 5 years, we'll see an petahertz electronics, yes.
Another question, please. Is the phototransistor going to follow the same rules for the natural transistor? Like, is it going to follow the same modes of operations for the CMOS technology, or are there going to be some changes regarding the modes of operation and the current drive and
I think there will be a little bit of changes, given the nature of the phototransistor is a little bit different, but the structure or the architecture may be more compatible to photonics more than
Hmm,
electronics. So this is what we will be talking about. We're not talking about electronics, we will talk about photonics. So it has to be compatible to integrate lasers, it has to be compatible to for controlling the stray light, the heat dissipation and stuff like that. But I think it will be less hassle than the semiconductor.
but it can be integrated in the electronics industry. Am I correct?
Yes, this is what we anticipated in the next few years. Yes. So there are people now working on optical computers. There are people now working in optical transistors and optical processors. It's already exists. It's not hugely spread, but it's already exists.
Nice. One last question before I see the questions the people asked. Um, what advice would you give to young researchers pursuing seemingly impossible technological advancements or breakthroughs, such as yours?
Can you repeat again?
What advice would you give to young researchers pursuing seemingly impossible technological advancements or breakthroughs? This, from 5 years, what you're saying right now would have been science fiction. However, you made it real.
Right, right. So the idea is, okay, I'm telling you a secret here. When we started this experiment, our idea was not about switching. Our idea was to enhance the conductivity of graphene. Okay, not this one, but when you search for something, keep your mind open for anything. And if you see an exciting things like this tunneling effect, try to explore more what's behind it until you get into deep of it, until you understand what's going on. And when you have a dream, just to try harder to reach us. And I'm just telling you, when we did the measurement of this particular experiment, we were not seeing anything. I mean, almost we give it up. But at a certain point, we said to ourselves, what about if we shine more laser? There are chances for damage. There are high chances for damage. But also, if we shine more laser, we may remove a layer of graphene, and this brings the silicon layer in and makes all of this. So
Hmm.
we will not be afraid to take risks. So taking risk is important. Yeah.
One last question. I'm sorry. I'm sorry that I'm taking too long.
Yeah.
Uh, why specifically did you pursue photonics? Not why.
Oh,
Yeah,
yeah. As
it's a
I
it's a bit personal question, I know, but
No, no,
I'm
no, no,
quite
no, no.
interested in it.
It's fine. My PhD was in photonics, right?
All right.
In developing a new laser, controlling electron motion, and this is all electronic. And again, particularly photonics, this comes from the title of our webinar, real life applications. And
Hmm.
real life applications of what I am doing is photonics.
Yes.
So I am always, yes, I am passionate about understanding new physics, but also I'm passionate to introduce a new technology to help in real life applications. So this is the main goal.
Right. Thank you very much, Dr. Muhammad. It was an honor having you with us today, and we've learned a lot from you. Thank you very much. Let me just see if the participants asked any questions. No, we do not have any questions. So that's all. Thank you very much. It
Okay,
was a
thank you
great
so
pleasure.
much. It was a pleasure to be with you guys. Thank you. Thank
Same
you.
here.
Thank you. Bye.
Have a nice day.